Hello everyone, my name is Syed Hanoof Ishaqi. I am pursuing BE in Electronics and Communication Engineering from ISL Engineering College. In this video, I will be discussing about tuned amplifiers from the subject Analog Electronic Circuit. We will be discussing its introduction, definition, classification, fundamentals, derivations, and etc. So let us start with the part of introduction. As we know, most of the audio amplifiers suffer from two drawbacks. First, they become less efficient at radio frequencies. Secondly, their gain is independent of signal frequency over a large bandwidth. Or in simple words, a normal audio amplifier amplifies a wide band of frequencies equally well and does not permit the selection of particular desired frequency while rejecting all other frequencies. However, sometimes it is desired that an amplifier should select a desired frequency for amplification. To accomplish this desire, tuned amplifiers are introduced. Now let us see the basic definition of tuned amplifier. The amplifier which amplify a specific frequency or narrow band of frequencies are called as tuned amplifier. Since tuned amplifiers are used for amplifying the narrow band of frequencies, hence they are also called as narrowband amplifiers or bandpass amplifiers. Next, let us discuss the need for tuned amplifier. The need for tuned amplifiers can be easily identified in the cases such as radio transmission and television transmission. In such cases, the transmission are carried on a specific range of frequency that is assigned to broadcasting stations. It is necessary to select a particular station among all the stations. Hence, frequency selection is needed, which allows the required frequency and blocks the unwanted frequency. The circuit which provides this purpose is known as tuned amplifier. By this we can even understand that the tuned amplifiers plays an important role in the process of transmission. The next, let us see the classification of tuned amplifiers. The tuned amplifiers are categorized as two types. First, small signal tuned amplifier and large signal tuned amplifier. Let us discuss each. Small signal tuned amplifiers. These amplifiers are used in amplification of small signals at radio frequencies and operates under class A operation. It is also called as RF voltage amplifier. And it may be further classified into two types: single tune amplifier and double tune amplifiers. Then let us see large signal tune amplifiers. These amplifiers are used for amplification of large power signals, and it is usually operates under class AB, B or C. It is also called as RF power amplifier. The use of class AB, B or C operation increases the harmonic distortion, but the use of tuned circuit eliminates response to these harmonic terms. So these were the classification of tuned amplifiers. Next, let us see the general considerations in tuned amplifiers. Whenever the tuned circuits are used, it is must to it to follow the following general considerations. That is, high selectivity and suppression of harmonics in tuned amplifier. Let us see what is high selectivity. A tuned circuit used in tuned amplifier must have the property of high selectivity. That is, it can select the desired frequency for amplification out of a large number of frequencies simultaneously impressed upon it. The second general consideration is suppression of harmonics in tuned amplifier. The impedance of tuned circuit and the gain of amplifier must be negligibly small at harmonic frequencies. Hence, harmonic distortion in tuned amplifier will be extremely small. Next, let us understand what are the fundamentals about tuned circuit. The fundamentals about tuned circuits are such as impedance, resonance curve, bandwidth, quality factor, etc. The figure shown here is a parallel resonant tuned circuit. A parallel resonant circuit consists of an inductor L and a capacitor C, which is connected in parallel to each other with respect to the supply source Vs. As we can see in the figure, this is the capacitor, variable capacitor, supply source Vs, L is the inductor, Here the resistor R represents the coil resistance. Its value is usually of the order of few ohms, and therefore it may be neglected as compared to the impedance of the resonant circuit. The figure shows a parallel resonant circuit connected across an AC source supply of variable frequency. Now consider the frequency of AC source is varied suitably. As a result of this, the circuit will encounter different impedance at different frequency. As the frequency is increased, the inductive reactance XL is equal to J2 pi FL is also increased, and the capacitive reactance Xc is equal to 1 by J2 pi Fc is decreased. At certain frequency, the reactance of inductor and capacitor will be equal. This frequency is called as resonance frequency, and it is designated by the symbol F suffix R. At resonance frequency, the circuit is said to be in electrical resonance, and the impedance of the tank circuit becomes maximum, and the line current, that is the current drawn from the source, is minimum. The expression for resonant frequency is obtained from the given condition, that is XL is equal to Xc. By substituting the values of XL and Xc as shown here, we get 2 pi FRL is equal to 1 by 2 pi FRC. By equating both and performing arithmetic operations on it, we will get a final value like this. Fr is equal to 1 by 2 pi under root Lc is equal to 0.159 by under root Lc in Hertz. If the value of inductance is in henries and the capacitance is in farads, then the resonant frequency is expressed in the Hertz. The second fundamental of tuned circuit is its impedance of tuned circuit. The impedance of tuned circuit can be derived as shown here by the help of admittance of inductive branch and capacitive branch. As shown, admittance of inductive branch is YL is equal to 1 by R plus j omega L, and admittance of capacitive branch is YC is equal to 1 by j omega L is equal to j omega L. The total admittance can be calculated by the equation Y is equal to 1 by Z is equal to YL plus YC. By substituting the values of YL and YC, we can form the equation such like this, and by performing some mathematical operations, we will get this type of equation. 1 by Z is equal to R by R square plus omega square L square plus j omega into C minus L by R square plus omega square L square. At resonance, the reactive component of impedance is 0. Hence, this whole term becomes 0. We will be left with j omega into C minus L by R square plus omega square L square is equal to 0 as shown here. And since omega is equal to omega R, we can replace omega by omega R. C minus L by R square plus omega square R L square is equal to 0. And we can replace the denominator term as omega R square L square. C is equal to L by omega R square L square. Then we can send this C to the right hand side and take this omega R square to the left hand side. We will get omega R square is equal to 1 by LC. Then we will send the square to the right hand side. It will become a root in denominator. Omega R is equal to 1 by under root LC. We have the value of omega R as 2 pi FR. So let us substitute the value, and we will send this omega R on the right hand side, as here it was in the multiplication form, and after going right hand side it will become division form. It will be in the denominator as shown. Fr, resonance frequency, is equal to 1 by 2 pi under root Lc. Then the impedance can be derived as 1 by Z is equal to R by R square plus omega R square L square is equal to R by omega R square L square. We can substitute the value of omega R here in this term, like 1 by under root Lc as we got it here. Then we can get 1 by Z is equal to R by 1 by under root Lc whole square L square is equal to Rc by L. Then by performing the cross multiplication and cancellation of the similar terms, we will get the final value as Z is equal to L by CR. The impedance of tuned circuit can be represented as Z is equal to L by CR. This formula can be used in the problems to determine the impedance of a tuned circuit. The next fundamental of tuned circuit is its resonance curve. A curve which shows the variation of circuit impedance with change in frequency is known as resonance curve. Here we can see two figures, figure A and figure B. Both are the resonance curve with respect to impedance versus frequency and current versus frequency. In figure A, the y-axis is the impedance and x-axis represents the frequency. Fr is nothing but resonance frequency. L by Cr is the value of impedance. In this figure, we can clearly understand that at the point of resonance frequency, the impedance is high. And in the figure B, the y-axis represents the line current and x-axis represents the frequency. Fr is resonant frequency, and at the point of resonant frequency, the line current is 0. It is clear from the figures that impedance is maximum at resonant frequency. However, the impedance decreases rapidly on both sides of the resonant frequency. This characteristics of the parallel tuned circuit provides its selective properties. In this way, a parallel resonant circuit selects the resonant frequency and rejects all the other frequencies. It is evident from the curve in the figure B that the circuit current is minimum at resonant frequency as the frequency is changed. Above or below the resonance, the value of the circuit current increases rapidly. Then let us see the next fundamental of tuned circuits, that is bandwidth. The bandwidth of a resonant circuit is defined as the band of frequencies where the impedance drops to 1 by root 2 or 0.707 of its maximum value at resonance. We have already discussed in the last section about the variation of circuit impedance or current of a parallel resonant circuit. This variation gives the tuned circuit an ability to discriminate between the frequency of resonance and those at other frequencies. This discriminating ability of a resonant circuit is expressed in terms of its bandwidth. Let us understand the figure bandwidth of a parallel resonant circuit. It is quite similar to the resonance curve. The y-axis represents the impedance and the x-axis represents the frequency. Zpmax and Zpmax by under root 2 are the values of impedance with respect to the frequencies FL and FH. Fr is the resonant frequency. The resonant circuit gives practically the same response as at resonance for this band of frequencies, which lie within the bandwidth. This band is also called the passband of the resonant circuit. It can be also called as the passband of the resonant circuit. Then, if the FL is a frequency corresponding to point A is here, and the FH is the frequency corresponding to point B, this point, then the bandwidth will be is equal to FH minus FL is equal to delta F. The points marked A and B on the resonance curve are known as half power points because the power developed at each of these points is half the power developed at resonance. Consequently, the frequency FL and FH are known as lower half power and upper half power frequencies respectively. An important note: when a constant current source drives such as tuned circuit, the voltage versus frequency curve and hence gain versus frequency curve have the same shape as the impedance versus frequency curve. Such tuned amplifiers are therefore used for amplification of a narrow band of frequencies. So by this we have successfully discussed the introduction, classification, needs and fundamentals about tuned circuits. So let us conclude here. I hope you like and understand the video. Thanks for watching. Thank you.